streaming. There we go. Alrighty. So I can recognize, quite a few familiar faces. So if you have taken classes from me before, there are some changes in this semester. I'm not using Moodle anymore because Moodle is going away next semester. Okay, whether I like it or not, it's going to be gone. So I'm switching to Canvas, but mostly only using it to organize the material. I am using a third website to house all the instructional material. So you will see, you'll see what's going to happen. So to use the LMS, you just go to Canvas. For those of you who do not know or you're new to AR or Lost Reels, to go to Canvas, you just type in Canvas, C-A-N-V-A-S, canvas.lostreels.edu. That's the URL to get to the LMS. It will be redirected to something else after you sign in. So your sign in is, mine is just my employee ID. You will use your own student ID. And once you sign in, it should appear as one of your classes unless you're on waitlist. So this section is 12429, which is this one. So when you get here, let me see if I can turn on student view somewhere here. I know I can do it. So.
I think it's in settings.
Under settings. Down there.
Keep going. Right above there.
There we go. And how come student view has glasses? But I have glasses too. So that icon doesn't mean anything to me. Okay, so this is student view. So when you get here, you just need to get to modules. And we have the syllabus as the first part, and then we have some instructional material as the second part. I'll be adding more stuff throughout the semester, so this is work in progress, but I will stay ahead of the class so that by the time you get to a certain topic, there will be reading material on the site. There's no textbook to buy, for most of you, you know this already. If you spot any errors, mistakes, or room for improvement, just let me know. And because these documents, I just change them pretty easily. Okay. Any questions up to this point? No questions. All right. So we'll go through the syllabus first, and I'm not going to spend a whole lot of time, hopefully, on the syllabus. The first part is just course information, stuff that I copied and pasted from the schedule. The key part here is the prerequisite. cisp310 is the prerequisite of this class, or 480. So you have to know your C or C++ up to a certain point to take this class. We don't do any type of object-oriented programming in this class. So if you don't use class inheritance, not a big deal. If you don't know what is an abstract method, not a big deal, and so on. But you do need to know your basic stuff. So I need arrays, structures, pointers. Okay, so with pointers, there are two things. You need to know how to, what is the meaning of taking the address of something, and what is to dereference a pointer. Okay, so those concepts are very important in this class, which is also why, for people who have taken Java, that does not fulfill the prerequisite of this class. Is that okay? All right. So the rest, is pretty typical stuff. Our final exam should be on the 12th of December, which is a Tuesday, and the start time is 8 o'clock. So remember that. Okay, in every single semester, I have at least one person thinking, oh, the class starts at 9 o'clock, so the final exam starts at 9 o'clock too. Nope, the final exam starts at 8 o'clock. Is that okay? So you might want to mark that particular date and the time slot in your schedule right about now. This part you cannot see from your schedule because this is actually pulled from the curriculum of this class. These are the things that you're supposed to know how to do, or these are the competencies that you will have after you have taken this class with a letter grade of C or better. Okay? And then we have the schedule of topics. It's only tentative, and I usually do not follow this very closely. Okay, so it gives you an idea of what kind of topics we need to talk about in this class. And it doesn't. Okay, I'm missing one link at the very bottom of this thing. So I'm going to go to my website and locate that here. That's the actual part of the. Okay, so this is a URL of my AWS-based server. I figured out how to get my own Debian server up and running using AWS or Amazon Web Service. Some of you might have played with it already a little bit. It's kind of cool. They have a deep learning AI engine as a backend that you can also experiment with. So it's kind of cool. But this is just a regular server. So this is the path, tilde TAUYUNG/teachers/modules. So this will give you a long list of all the things that I have written from like many years ago. The syllabus is the last module, so it's 0286. I'm going to put the link into the syllabus part so you don't have to remember this. But this is the format of most of the documents that I'm going to write in this class. So most of those will give you two formats. You can download and print the PDF if you want to have a paper version, or you can just use the HTML version if you want to view the content using a mobile device or on a computer. In a class setting, I always prefer to use the HTML version because I can zoom in, I can zoom out, it just looks better on the screen. All right, so here's a little explanation why this document is not on an LMS, because over the past 14, 15 years, this is the third time that we are changing the learning management system, counting the Blackboard as the first one. So I don't want to make my content dependent on the LMS anymore, because I don't want to reinvent the wheel every single time they choose to use a new LMS. So this content is hosted completely off of the LMS, and so that's the reason I don't want to have to redo the things all the time. And the purpose of this document is really just this is a part of the syllabus, but it is common to all my classes, so it doesn't make any sense to copy and paste this into multiple documents. In other words, this is a super class. Nobody's getting it. You saw the subclass earlier. This is the super class. So my name is Tak Aoyoung. Just call me Tak. It's cool. My last name, even if you can't pronounce it in English, it's not even close to the Cantonese version. Okay, so it's okay. However you want to pronounce it, as long as it's not offensive. Just call me Tak. Tak is cool. Okay. No, Tak is not cool, but calling me Tak is cool. I need to make that differentiation so that people don't say, what, Tak says in his own class that he is cool. No, I said calling me Tak is cool. See how ambiguous natural language is without the nesting, the parentheses, to indicate which part applies to which part. I hate it. Okay, so my email address, I'm switching back to just using the Exchange email address, so it makes it easier. In certain cases, my office has moved. Okay, so some people still remember that I'm in office number 7. I'm now moved to office number 3 in liberal arts. So my office got bigger, and I think I can easily fit about 2 to 3 students in my office, so we can have small group discussions and stuff. Office hours is very good for this class because it is Monday through Friday, including Tuesdays and Thursdays from 8 to 9, which is right before this class. So if you just arrive on campus a little bit early, you can stop by my office, we can talk about stuff, and then we walk over to the class together. Presentation slash delivery methods. This is a face-to-face class, so most of the stuff is going to be done through face-to-face lectures. I don't really use persistent video clips, but I need to include this clause because the distance education part of the campus is making sure that all the syllabus or all the syllabi from everybody are compliant to the college requirements. So this part is supposed to be here. If I do have any persistent video clips, they will have to be closed captioned. Reading materials are in HTML and PDF distributed through my own AWS server. Interactive activities can include course material, and these are distributed through the current official LMS, which is Canvas at this point. Any questions? No? Okay. Section 6, once again, is just a college policy. Everybody is supposed to have this section in the syllabus. A face-to-face class usually doesn't have regular effective contact. Okay, this is actually a typo. Regular effective contact issues. This applies mostly to online classes where a professor can just click a switch, okay, click a button, and reset the class to start on a certain date, and just let the LMS run the class for the entire semester. Because someone can choose to use homework assignments and quizzes that can be self-graded or at least automated in an automated way. Okay, so in order not to have regular effective contact with a face-to-face class, I will have to write on the whiteboard like this and talk like this for the entire class. And if you guys have any questions, I will have to ignore all the hands and all the questions. Then I will not have regular effective contact. If I answer your questions, I have regular effective contact. If I have eye contact with you guys, I have regular effective contact. If I'm in the classroom, I have a little bit of regular effective contact. So these are mostly applicable only to online classes. But I do have to show you, where you can find me, my office hours, email and phone. But the best way, as far as the college is concerned, if you need to contact me, they prefer to use texting and messaging for accreditation purposes, because this will leave behind a log on the server, so that the next time we have accreditation, we can show the log to the ACCJC, which is the organization doing the accreditation, and say that yes, we have a log of how the professor interacts with his students. Are we okay so far with all this stuff? Okay. Time frame policy: 24 hours in general, but about 24 hours over 48 hours over the weekend. Etiquette policy. I'm not really big on manners or etiquette, so the bottom line is, I just want to make sure that the classroom, both online and face-to-face, remain as a safe environment and effective environment for everybody to learn and for me to teach. That's the bottom line. I mean, I don't really enforce a lot of stuff, as far as etiquette is concerned. Okay, so just make sure it's not hostile or can reasonably lead to interpretations of harassment or discrimination. In other words, the key word here is interpretations. In other words, the person who is saying something may not intend harassment or discrimination, but if the person who is receiving can reasonably interpret it as harassment or discrimination, we don't want it, with the forums or in the classroom. Okay. Cyberbullying is bullying, and it's not going to be tolerated. Spamming is, I see that as a form of denial of service, and this is also not going to be tolerated. Offensive content is not going to be good, so mostly just common sense. First day of class or orientation, which is this class. Since you guys are here already, you don't have to worry about it. Okay, it's people who are missing today that will get dropped. Now, that being said, the screen recording is actually being streamed onto YouTube with a delay of about 20 seconds. So I can actually see somebody maybe watching this, somebody who's actually on my roster is watching this on YouTube right now. So if you are that person, you're in big trouble. I'm just kidding. I don't think anyone is going to do that. Accommodations. If you need disability accommodations, you don't need to let me know, but you do need to let the DSPS office know about it. This is the phone number. If you need to know where they are located, you can read the map of ARC or ask me or ask anyone to find out the location of the DSPS. Excessive absences. 6% or more absences is considered excessive. So once you do all the math, this is the bottom line, okay? Each class accounts for 2.47% of the contact hours in this class. So that means, the third absence that is unexcused, it will be considered excessive. So you have 2 absences that you don't have to be excused. Okay, you can say, I just decided to take a day off for no particular reason. Fine, you get 2 of those days. But I will keep those days, I will keep those 2 days for uncontrollable events, like my car wouldn't start. Yep.
What counts for an excused absence? What counts for an excused absence?
Sickness with a doctor's note. So if you're sick, you go to a clinic, and the doctor says, well, yep, you're really sick, should not go back to school for an entire week. Then you have that excuse to miss, like an entire week. So those absences would not be counted to your excessive absences because they are excused. Okay. All right, so that's the bottom line. I'm moving on. Excused absences, which is exactly what you asked about. So the only absences that are guaranteed to be excused would be a student's own health-related absences that has a doctor's note or some kind of evidence or documentation. Okay, is that okay so far? Okay. So there's a whole long list of everything else are unexcused. So we include religious holidays, family occasions, job interviews, work-related issues, going to Oregon to watch the eclipse, that sort of thing. Well, I actually got people, not students, I got faculty members, who told me last week that go like, you know what, Tech, I want to drive my family up to Oregon to watch the eclipse, and go like, you're not going to be able to find any place to stay this late in the game. And go like, well, maybe the only chance is to rent a RV from California and drive all the way up, to watch the eclipse. But that's a lot of driving just for a few minutes of watching the eclipse. Okay, late policy is easy to remember. There's none. I do not take any submission late. Anything that's turning late won't get any points. It's kind of harsh, but easy to remember. And easy to plan for too. Because you don't have to remember, okay, wait, hold on a second here. How's Tech going to treat my late submission? Is it like 20% per day, or is it a exponential decay, or what? No, there's no point. Don't turn in things late. Is that okay? All right. I typically give you a week on most homework assignments, and if the class in general is having a really, really hard time, sometimes I will give extensions. Okay, but usually it's not going to be a big surprise. It's like, you know what, I'm going to have a homework assignment due on Thursday, like 2 days from today, and it's a really, really, really hard homework assignment. I don't do things like that. I will give you a homework assignment a week ahead of time, and then I'll talk about it. Those of you who have taken classes from me know that I usually start with the homework assignment, and then I'll proceed to talk about the topic that you need to know to get it done. Okay. All right. Academic dishonesty, the bottom line is this. Okay, the bottom line, if I were to summarize all of this, is when somebody intentionally try to show a competency, knowledge, or skill beyond the actual level of that person, that is cheating. Okay? Any questions about this kind of general definition? Nope. All right. Now, if somebody is showing competency lower than the level of that person, it's okay. I don't have a problem with that. In fact, a lot of people will confess and go like, Tech, you know what, I think this score is much lower than what I should be getting. And that's not dishonesty, that's okay. So the other way to look at this is from the integrity perspective. So the score or the points a student is getting should be of the student and only of the student who turned in the assessment at the approved time, following all the instructions, and only using the resources that are allowed by the instructor. Okay, pretty common sense stuff. And the limits test means, if I want to confirm whether somebody is turning in a homework or a test and not using somebody else's help, I can ask a person to take an alternative test or do an alternative homework and see whether that person can be, whether there's consistency between the two assessments. So if there's a big discrepancy of performance, then I have reasonable doubt. Otherwise, if they're about the same, then we're like, okay, sorry, my bad. Okay, so these two sections talk about why academic honesty is important, not only to me, but also to everybody. And also the consequences of people who were identified with cheating and related stuff. This is a link to a document that would show you or tell you what to do if you feel that you are wrongfully accused. Okay, you have rights. Okay, if you feel that you're wrongfully accused, what do you do about it? Okay, who do you go to talk about it, and what is the procedure to file grievances and so on and so forth. So that's kind of a useful document. Classroom behavior expectation, kind of the same stuff as etiquette for communication, but for the most part, I just need to make sure that there's not a whole lot of chatting in class. Most of the time when people chat in my classes, it's not just chit-chatting. It's mostly because one person did not quite catch what I said, and was and is asking the next person is like, okay, what did Tech just say, or did you catch what he was saying, or ask for explanation. So if it is class related, just go ahead and ask me. Okay, raise your hand, and ask me instead of the student next to you. Okay, because that way, the student next to you won't be distracted. People who are around you won't be distracted, and the class gets to breathe a little bit, because now I have to stop or slow down to explain something, and everybody will thank you. Is that good? Okay. Interrupting. So if you do have a question or a point to make, just raise your hand first. I do not know that I have any cases of ignoring people who have something to say in my classes. So I usually just kind of take turn, and let people talk, whatever they want to talk about in class. Keep your mobile devices silent during class. Android, I'm not sure about iOS, but the newer versions of Android, they have a do not disturb setting that can tie into a calendar. So if you mark the time slot in the calendar as a class and mark it as busy, you can make the do not disturb feature to use that as a rule and say, okay, during any type of scheduled time slot that is marked busy, turn off the ringer. Okay, it's pretty nice. I mean, it turns it back on, after the class, so you don't have to remember to turn it back on. There's a sign at the back of the classroom that says no food, no drinks, no phones, and no kids. Okay. To me, you can have plain drinking water. Okay, because you don't have a computer other than your own in front of you. So if you spill water on your own computer, well, you need to check the warranty or extended warranty of your computer. But anything that's clear, liquid, just your plain water would be fine. Okay, and I have my own here. I just have to drink it away from the keyboard. Otherwise, if I do any type of spilling over here, Gerald would have a conversation with me. Let's see, how to attend lectures. So the first part is I usually record all my lectures. There's a screen recording that you can find on YouTube. It is a good idea to check, did you turn on the recorder? Are we streaming? And also check to make sure that the mic is on, because sometimes I forget to change the mic setting so it will be silent. But given that I'm recording, the best way to attend or to be here in my lectures is not to busy copying stuff. Okay, instead, focus on what I'm saying and think about, okay, do I have any questions about that? And just ask questions whenever you have questions. Okay. Any questions about that part? Comments? Okay. If you want to effectively use the screen recordings, you might want to jot down like a timestamp of when I start to talk about something. So let's say later today I'm going to talk about different types of transistors, okay, and how to use a transistor to make a logic gate, okay. So that's a pretty important topic. So you might want to jot down the time and go like, okay, it's right now it's about 9:50. Let's say at 9:50 we start to talk about that topic. So you might want to jot down 9:50 transistors turning into gates, okay? Because that will help you locate that part of the notes or the screen recording when you're watching the YouTube clips. So that you don't have to linearly go through the video clip to locate a particular section. How to succeed in this class? Section 16 is really, really long. It talks about why understanding of the material in this class is really important. I don't test whether you can memorize stuff. Okay, I can tell you already the first, the second, and the third, and the final exam, they're all going to be open book, open notes. You can bring anything that is handwritten or printed. If you find a particular screen, on YouTube to be really helpful, you can take a screenshot and print it out and bring it with you to the exam. You can bring your homework assignment to the exam. You can bring my solution to the exam. There's no limitation of what you can bring as long as it is on paper. Okay, so that means you don't need to memorize a whole lot of stuff. What I do test is whether you understand the material and be able to apply the material, the knowledge, and be able to problem solve. So that's how I test, in this class. Okay. So this whole section talks about, what is understanding, understanding. Okay, that's another recursion right there. It's meta understanding, right? There's also how to apply a concept. Okay, what if I cannot understand a particular concept? And the key point of this is don't move on. Okay, don't just say, this is probably not important. I'm just going to continue to read the notes or continue on with the class. Okay, if you have something that you don't understand, you have to ask questions, especially if you realize this is something that I'm not getting in class. Then you want to stop me and go like, okay, can you explain this in a different way? Okay, or you can confirm with me and say, okay, let me just check with you. Okay, this is my understanding of what you're talking about. Okay, so this way, you can double check with me in class to make sure that your understanding is correct. And once again, the rest of the class will thank you. Okay, because without questions, without somebody to slow me down, sometimes I go a little bit too fast. So, it's always good to have, these questions. Problem solving is the application of what you have learned to solve a problem. Okay, this section has to do with how independent should you try to be when you are working on your homework assignments, or when you're reading the material, or when you're studying. Okay, in other words, the question is, should I ask someone after 1 minute of reading the material? Go like, I'm not getting this. I'm gonna ask somebody. Okay, do you wait 5 minutes, half an hour, a day, a week, a whole semester? So, it's here. You can read about it if you want to. If you don't, think this is important, you don't have to read about it. But go ahead.
Do you accept emails about clarification in that sense?
About
understand a certain topic that you're covering, but you're away from class and you need to you don't have anybody to reach out. Can we send?
I will get back to you in 24 hours. As per the communication policies. So if you're asking me a question over email, it really helps to identify who you are, especially when your Gmail username does not indicate anything about your actual name. You want to talk. You want to let me know which class you're in. Okay. Now I have 2 sections of cisp310. So
use the code?
Huh?
Do we use the number code? Is that better?
Your student number?
Instead of putting Monday, Wednesday, or Tuesday, Thursday.
Monday, Wednesday is fine. MW or TT. That will work just fine. And your question has to be specific. Now, if somebody says, I'm not understanding the material, can you explain it again through email? I would go like, not really. Can you tell me exactly what you're not understanding that I need to explain in a different way? So the more specific you make your questions, the faster I can come back with an explanation or an example, or tell you, okay, look, read this page here, that might be helpful. Okay. And studying before attending a class is also helpful so that you know ahead of time what kind of stuff I will be talking about. Grading standard, I'm going to skip the first part here to the letter grade equivalency. So what is an A, what is a B, what is a C, what is a D, and what is an F? Okay, there we go. So the first row talks about the short description that you guys know already, okay? Because most colleges or universities or even high schools would use this particular standard. They would describe an A as excellent, a B as good, a C as satisfactory/fair, a D as a low pass, and an F as a fail, okay? So we know these words already, but what does it exactly mean when I am going to score your test or homework assignments? An A basically means you are giving me a perfect answer. I cannot, there's no better way to do it. Okay, as far as the context of the question is concerned, there's no better way to do it. A good answer is one that is mostly correct, but with some flaws. Okay, it can be a minor mistake, can be some minor omissions, but it does show that whoever is turning that in understands all the concepts, is able to apply the concepts to problem solve. It's just that, be a little bit more careful, or tell me a little bit more. I need the answer to be a little bit more complete. That would be a B. A C would be something that has major flaws, major mistakes, major omissions, but it still barely, sufficiently show understanding of the concept. A D would be an answer that sort of shows some understanding, but not enough. And an F means there's no answer, or the answer does not show any understanding of the topic at all. Is that okay? I know it's kind of fuzzy, because these are all kind of words describing something. On your own time, you can read the other ones. So in terms of a job evaluation, what is an A employee? What is a B employee? What is a C employee? What is a D employee? And what is an F employee? Okay, so I'm just giving you some alternative ways to understand how I look at A, B, C, D, F. And the last one, product evaluation, is something that we all understand. Okay, unless you have never gone on to Amazon to read product reviews and stuff like that uses the star system, you know what kind of product is a 5-star product. Okay, execution is perfect, quality is perfect, good value for what you're getting, and so on and so forth. In other words, you cannot ask for anything more. A B product or 4-star product would be a good product. You will still recommend it to your friends, except, well, if I can tell the manufacturer to improve, okay, these are the minor things you can improve on the product, but otherwise it's still a good product. A C means, it is acceptable, I'm getting, it's okay, okay? I may not recommend it, but I'm not returning it either, okay? It's okay. A D product, which is getting 2 stars, is kind of like, if I could, I would like to return it, but I don't, maybe not go through the hassle to return it. But I'll definitely not recommend it to somebody else. I'll tell other people and say, don't buy this, okay? I bought it and I regret it. A 1-star product would be something that you definitely do not want to buy again, do not want to recommend, and you want to return it. Is that okay? So this is how I look at A, B, C, D, F. And the second last row you know already as well, because those are the center of the GPAs of those particular grades. So an A is a 4.0, a B is a 3.0, and so on. You know that stuff already. So the last one, which is a percentage range, is what you really want to know, because that tells you that if you get at least 87.5% of all the possible points in this class, you get an A in this class. If the amount of points that you get is somewhere between 62.5% to 87.5%, you get a B. And to pass this class with a letter grade of C or better means 37.5%. Okay, but it doesn't make the class easier than the other classes. Okay, many of you have taken classes from me before. Would you say it's easier? My classes are very easy to get a good grade. Yep, exactly. I just want to give people plenty of warning ahead of time so that people don't get the concept going. Wow, I just need 37.5%. It's easy peasy. No, it's not. Trust me. Now, at the end of the semester, if you really think it's easy to pass this class or get an A out of this class, you can just tell me at the end of the whole semester and just go like, Tag, you lied. This class is easy peasy. Ha. That's okay with me. As opposed to the opposite and go like, Tag, you told me this is going to be an easy class, but I didn't get a good grade. What's wrong with it? So you don't want to explore the possibilities of less than 37.5%, but it's listed here. Anyone who's getting somewhere between 12.5% and 37.5% is getting a D, and anyone who's getting less than 12.5% is getting an F. Whew. Okay, any questions about the grading standard, how the score translates to letter grade at the end of a semester? Okay, questions? Nope. Okay. Yep, go ahead.
So it's just, will you update the grade consistently, or going to be like once a month, once a month?
I'll try to be, efficient in grading. Grading homework assignment is one of the most boring things, for a professor like me. Some people like doing that sort of thing. I have to drag myself to do it. So yes, but I will try to do it as quickly as possible. The homework assignment, which is going to be shown next here, the homework assignments are not going to be contributing that much to your grade. So homework assignments only contribute to 20% of your final grade. The purpose of the homework assignment is to let you practice what you have learned and apply your problem-solving skills. So by problem solving the homework assignments, I'm hoping that people would actually learn the concepts and know how to apply those concepts. That's the major value of the homework assignments, not the points. Okay, so, and I'm expecting most people to be able to get close to 20%, maybe 15 to 20% with the homework assignments, because there are no really big surprises. You're not that constrained by time. Most homework assignments are due in a week. So I'm not really thinking that people would miss too many points in homework assignments. The exams, the midterms and the final exam, those are the kind of bigger items. There are 3 exams in this class. The first midterm is about 1/3 through the semester. That's 20% of your grade. In other words, one single midterm is carrying the same weight as all of the homework assignments. Okay, Okay, so if you're missing the homework assignment, missing a few points, but you learn from the homework assignments, you may be better off than people who copy from somebody else's homework assignment and completely miss, completely not be able to answer the question in a midterm. So try to do the homework assignments as independently as possible, because that's how you learn the concepts and learn how to apply the concepts in this class. Okay. The second exam is about 2/3 through the semester. That's also just another 20%. The final exam by itself is 40% of the final grade for this class. So that's kind of important. Okay. Are there any questions about how you will be assessed in this class? Yep.
Do each exam is built onto the next exam? Like you need to know parts of the first exam in order to get better score on the
Yeah, there's an implied dependency of material in this class. So it's not going to be explicit. Most of the time, in the second exam, I'll be focusing on the material that I teach after the first exam and before the second exam. But because the knowledge that you're building on in this class is kind of like stacking, so I can't really just test concepts strictly, from after the first exam to the second exam, because those concepts depend on the concepts of earlier. But I may not ask you explicit questions for those earlier topics. But by implication, you still need to know everything that you already understand. Okay? Are there any questions about the syllabus? This is it. I'm not trying to spend the entire class on the syllabus. No questions? Cool. All right, so with no questions here, I'm going to get started with the actual part of this class. Okay, so as I said a little bit earlier, all the material in this class are distributed in this particular form. There's a PDF and there's an HTML document. So this slide or this module, okay, a document is called a module, talks about physical states, truth, numbers, and computers in general. And this is one of very few classes where we actually care about the physical state of a computer. Why do you think it is important to understand, the physical implementation of computers?
Might build up.
Exactly, because otherwise you can think about, oh, it'll be kind of cool if we have this kind of material that can do that, so that we can implement super duper computers. That's all nice theoretically, but it doesn't actually tell you how to make a computer, right? Okay, so that's why, in this class, we kind of talk about physical devices a little bit. In the good old days, computers were electromechanical, which means they have motors, rotors, and stuff like that. You can actually see things moving. And those are electrical devices that move. So it is both electrical and also mechanical computers. But as you can probably imagine, these devices or these computers tend to be pretty slow because of the mechanical aspect of that. It's just like when you compare an SSD, a solid state drive, with a magnetic drive. Okay, there are big differences. Why? Because a magnetic drive is mechanical. There's a long delay to go from one track to another track. Once you're on a track, you have to wait for the right sector to go under the head of the drive. So there are mechanical delays that you just cannot avoid. But an SSD, just like that, right? Because there's no mechanical movement. There's no delay due to mechanical movements. So electromechanical computers tend to be bulky, energy hungry, and very, very slow by today's standard, okay? But they're still useful because at the end of World War II, the German Enigma encryption machines received a fourth wheel to scramble broadcast communication. The British had a way to crack encryption by hand before the fourth wheel was introduced. They could do the decoding, the deciphering fast enough to be useful. But once the fourth wheel was introduced, it became kind of too complicated to crack manually. by the time it is cracked manually, the value of the message is gone already because the event would have happened already. So they had to use a computer to automate this process and do it much faster than people could. Okay. So for those of you who have not watched the Imitation Game, you can watch that movie, which is partially based on history. There are a lot of disputes of the accuracy of the math, the computer science part of it, of that, and also even the personalities of these people, the historical figures. But it's a movie, it's entertaining, and it is sort of, it will give you an idea of what this is talking about. So next, we move on to vacuum tubes. Here's a link to a vacuum tube description in Wikipedia. And vacuum tubes, they look like light bulbs. Inside is almost vacuum, and they have layers, cylinders, layers of cylinders of plating, okay, and it relies on electrons, to travel through vacuum from one place to another place. That's the basic mechanism of a vacuum tube. Okay. They are not mechanical devices. So the first thing that we understand now is, vacuum tube computers are faster. They're much faster because they are solids. There's no mechanical aspect to it. So they're much faster. But in order for vacuum tubes to work, you need to heat up the filament. Okay? And heating of filaments means, consumption of energy. And you cannot make them too small either. So vacuum tube computers are faster, but they are still pretty big and power hungry as well. So we are talking about using a lot of energy to do some computation. I'm not going to ask you guys to talk about the mechanism, like what is a triode of a vacuum tube, but the bottom line is, well, they're kind of cool, and they were actually in use already at the end of World War II. Once again, it is for deciphering messages, but this time it is for deciphering messages that were encoded by the Lorenz cipher, which is a different cipher compared to the Enigma cipher. This one is not portable. It's not like a little typewriter, like the Enigma machine. You can just take it to the field. This one is pretty big, okay, and it's only used for the highest level of communication in Germany back in those times, okay. But it's much harder to crack as a result. And the Colossus was a computer made out of vacuum tubes, so that it is fast enough to deal with this kind of message cracking. Is that okay? Right? So then we move on to transistors. Okay, the whole concept of a transistor is it is made out of semiconductor materials. Now, semiconductor is kind of a strange name. Is it conducting or is it not conducting? Or is it just sort of conducting? Okay? Well, the best answer I can give you is the conductivity of a semiconductor is controllable. Sometimes it's not conducting, and other times it is. Okay? So it's basically a valve. Okay? Look at a semiconductor device as a valve, where you have a control signal, and you can say open the valve so that it can flow. Electric current can flow, or you can turn it off so that it is not going to be on. It's not going to allow flow anymore. The actual physics of this, we're not going to put too much attention to it. It's all based on p-n junction. It doesn't really matter whether it's a BJT type of transistor. BJT stands for bipolar junction transistor, BJT, or MOSFET, which is metal oxide semiconductor field effect transistor thing. So it doesn't matter whether it's a BJT or a MOSFET, they're still kind of based on a p-n junction. There's no need to understand what a p-n junction is. It's a relatively complex and strange concept. Okay, if you're new to electrons and holes and how these things exist in semiconductor material, you don't have to understand it. Okay. Yep.
Wasn't it just referring to positive, negative?
But it's not just that. Okay, because when you can have a p material and an n material. By itself, a p material is conducting. By itself, an n material is also conducting. But by applying, a electrical potential to the two ends, you can have a zone at the junction where it is neutral. It's neither P nor N, and that becomes the insulation, and current cannot pass anymore. So it's kind of complex because all of these things, the zones can move, they can get wider, then they get narrower, and so on. I remember when I was in 4th grade, I was reading a book that answers all sorts of science questions, and I was stuck with PN junction for at least a good 5 weeks. I was stuck on like 2 or 3 questions that talk about PN junction, and there were like 4 or 5 weeks where every single day I would read it a little bit and try to understand it, and it took me like weeks just to understand the general concept, not even the math, of how a PN junction works. But it's cool. Okay, so what is the bottom line? The bottom line is transistors they don't need to be heated up. In fact, they hate to be heated up. Okay, so you don't have to spend all that energy just to heat up a vacuum tube. Well, that's good. We are saving power. Number 2, they're very small. Okay, we are talking about, because for a vacuum tube to work, you physically need to have a heating filament in the middle of the vacuum tube. You need to have a plate where electrons can be emitted, and then you have at least one more on the outside to collect the electrons. A transistor doesn't do it like that. It's on the surface. It's on a wafer, and you can basically print the circuitry onto the wafer, and that makes your transistors. So they can be made very, very small. So the question now is this computer, are these computers using transistors? You betcha, okay? But Tech, I heard about these things using chips and ICs and stuff like that. Those are not transistors. Well, they are transistors. It's just that on a single wafer, on a single unit, you are packing millions and millions and millions of transistors onto like something like that big. Okay, you can find out the exact number. You can just type in Google and say, okay, I7 transistor count. Okay, I'm pretty sure the first 2 links will give you a number of. Okay, it varies depending on which variant of the processor you're dealing with. But does anyone know the order of magnitude? No? Okay, I'm curious. I gotta find out. Okay, I7 transistor count. There we go. There you go. So just in general, this is 2012, an 8-core AMD processor has about, that's billion, right? 1.2 billion, and a quad-core Intel processor in 2010 has about 1.4 billion transistors. So we are already in the range of billions, not just millions. Okay? So how big is one transistor? What is the dimension of one transistor? They're now in 14, I think that the current generation that you can buy is about 14 nanometers, okay? Which is really, really small. Okay? And every single time, how many people have heard of Moore's Law? M-O-O-R-E, Moore's Law. Okay? Which says the density of transistor doubles every 18 months. Okay? And there were many times throughout history that they thought that they have hit the limit already. And I'll give you this one single example, but it kind of shows you how we always find ways to pack more transistors. This is back in the 90s, early 90s. So I would say between 92 and 93-ish, okay? My roommate, who was a WE student at UC Davis, had a call sign or username in one of the online games, and his call sign was submicron. SUB sub, which is smaller. Micron is a micrometer, which is a millionth of a meter. Okay? So he has a name of submicron because at that time, people thought it would not be possible to make transistors smaller than a single micron. Okay, so having a name of submicron seemed pretty cool. Okay, it's kind of like a few years before we called everything giga something, right? And then before that, we called stuff mega something, like Mega Godzilla. Okay, but now giga doesn't sound very cool anymore, right? Because everybody has gigabytes in, at this point. Your hard drive easily have what, 3 or 4 gigabytes, terabytes of your hard drive space. So being giga is not cool anymore. Now it has to be tera, right? So back in those times, they thought that transistors cannot get smaller than a single micron. So fast forwarding to 2017, which is around 22, 24 years, after that, now we have transistors about 50th of a micron. And you might think, oh, 20-something years. Hey, that's my age. Your age, right? Some of you are probably in your 20s. It's like, oh, that's a long time. Nope, 20-something years is not really that long of a time. If you compare a car, okay, like 24 years ago, and compare to a car that is manufactured yesterday, okay, the improvements are not really as as dramatic, okay. Yeah, you get better fuel mileage, gas mileage. You get more power out of the engine. Emission is better. Everything is better. But by that much, 50 times, I don't think so. There's nothing that I know of can improve, have a 50-fold improvement in 20-something years. Okay, so kind of putting things in perspective. This is the kind of stuff that we are dealing with. All right, so physical states are important because we kind of we have to assign quote-unquote meanings to physical states. Now the good thing about modern computers is that they're all digital computers. And not only are they digital, they are binary digital too, which means we only care about zeros and ones in all of these modern computers. Okay, we don't really care about the in-between states. So something is either on or off. Well, if it's either on or off, we can now arbitrarily assign a meaning of true to one state, and the other one will get a meaning of false. Now, that's just completely arbitrary, okay? You can say high voltage is true, low voltage is false, or otherwise, it doesn't really matter which way, because it's just that one is one meaning and then the other one is the other one. All right, so the next one, section 3 is really kind of important. This is where the itty-gritty detail starts, okay? So at this point, we'll actually introduce, a certain type of transistor, or 2 types of transistors. One is called an N transistor. This is an N transistor. It looks like this. And this is a P transistor. It looks like that, okay? Can people in the back see both transistors? You guys okay back there? Okay. I can actually zoom out just a little bit so that we can all see both of these transistors. What is the first thing that you notice that is different between these 2 transistors? The arrow points into different directions, but we can always rotate it and mirror it so that it points in the same direction. The dot, okay, very good. So the dot right here is the only difference that you can rely on to tell these 2 apart, okay? P transistor has a dot, and N transistor does not have a dot. Okay, but what does that mean? Well, a dot in schematic means negation. Okay, a dot means negation. So that means, okay, remember 2 things. A dot means negation, and a transistor is a valve that has a control signal. Is that okay? So without the dot, which is the N transistor, when the input voltage is high, the valve is turned on. It connects. Okay, let me say that one more time. For an N transistor, because of the lack of a bubble, the input is not negated. A high voltage at the gate, which is the line coming in from the left-hand side, is going to turn on the transistor. When the transistor, which is a valve, is turned on, it allows flow. It connects one end to the other end. Is that okay? Well, that makes a P transistor just as easy to understand. It's just negated. So when the input voltage is high, the transistor is turned off. So the valve is off. It does not let flow through. The only time when a P transistor is turned on is when the gate voltage is low. So when the bubble is experiencing a low voltage, that is when the device is turned on and allow flow to go through. Is that okay? All right. So given that, yep.
Yeah, I just have why are they why is the negated one the P transistor and not the N transistor? That really bugs me. Do you know like what it stands for? Why?
Well, the P and the N represents the main material of the transistor, the substrate material. So for an N transistor, it can be an NPN BJT, which is a like it has. Okay, so because you asked a question, I'm just going to briefly answer that. So an NBJT is an NPN transistor. So you have N, P, and N here. The two ends would be the flow that you're controlling, and this is the control signal here. Okay, but the substrate is an N material, so the majority of the transistor is made out of N material. If you have an N MOSFET, then you have the substrate itself being an N material, and then the P material I think is here, and then you have the insulation here. So this is the gate. One side is the source, the other side is the drain, which is not important in our discussion. But these are the two terminals of the flow that you're controlling. This is the signal controlling the valve. And this is an N transistor, but it's an N MOSFET, a field effect transistor. And the idea is, the gate voltage would affect the P material here, so that, and also the N material. So if the gate voltage is low in this case, then the N material would actually be affected by the P material, and it will be neutral about here, and so it is not conducting. But when there's a high voltage here, then the N material will become N material again, and as a result, current will flow through. If you're going to take a device physics class at any four-year university, they will explain the actual physics and all the math behind all of this stuff here. But for us, it is just logically, how do we utilize the transistor that is important. Is that okay? Yep.
So like N transistors correlate to high voltage, and then P transistors correlate to low voltage, right?
An N transistor is turned on by a high voltage at the gate. A P transistor is turned on when the low voltage is presented at the gate. Right, so given the basic properties of these transistors, what do you think this is going to do? Well, first of all, let's check it out. Okay, let's check out how it is made up. Okay, we have Q1, Q2. So for some reason, the letter Q is usually used to designate transistors in a circuit diagram. So we got Q1 and Q2 being what type of transistor here? The P type, because they have a bubble. And then we have Q3 and Q4 being N transistors because of the lack of a bubble. Yep.
It's barely visible though.
They're what?
It's barely visible.
You zoom in on.
You mean the bubble?
No, the whole image.
The whole image?
Yeah.
We can zoom in a little bit. Would that be better? Okay. So the direction of the arrow is correct. Okay, it looks like it's backwards, but they're actually correct. Because for a N-channel MOSFET, the source is the lower voltage, and then the drain is where it can go. For a P MOSFET, the flow goes from the high voltage, the source is the higher voltage, and then the drain is where it can go. So the triangle at the top is representing what we call the power, or VCC, or some kind of positive voltage. Okay, that symbol represents a higher voltage, a source of a higher voltage. This ground symbol represents 0 volts. Okay, so so I'm going to use the whiteboard just for this illustration. So if you're looking at a AA battery, okay, it looks kind of like this. This part is the positive voltage. This part is the 0 volt or the ground. Okay, so that's basically an idea of to relate something that you know to the symbols in the schematic. Is that okay so far? Okay. Okay, so now we have all these, kind of darker, bubbles. So when you see a dark bubble like this, it is a junction, which means whatever is coming from X is going to the gate of Q1, but it's also going to the gate of Q3. But when you see a junction but without the big dot, like this one here, they are not connected. These two wires are just flying over each other, so they are not electrically connected. Is that okay? So now I have just described how to read a schematic in general. So the question now is, what is this thing going to do? When the square pins are input pins, and then the circle pin is an output pin. In other words, you can control the voltage presented to X and Y, but you are going to observe the voltage at the bubble, at the round pin. Is that okay? All right, so we're going to play out a few scenarios. I'm not going to play out all of the scenarios because two scenarios should be enough to illustrate how this works. Besides, the notes actually contains all the scenarios. So you can read about this, but I'm going to show you how it works. Okay, let me move this to the other window. Put it here. So the way you analyze a circuit like this is to say, okay, let's figure out, okay, X and Y are basically your independent variables. In other words, this is where you say, oh, let's say X is low, Y is low, and see what happens to the whole circuit, okay? And then you want to look at Q1, Q2, Q3, Q4. Look at the states of those transistors, and then you look at the output and go like, okay, what is the voltage presented at the output pin? So these are the columns of a table that we're going to make here. I don't know. Let's try low and low. Okay, I'm going to use 0 to represent low voltage and 1 to represent high voltage. Is that okay? Just symbolically, I'm not writing LO or LW. Just use 0 to represent it. Is that okay so far? Okay. All right. So if X is a 0 or low voltage, is transistor Q1 turned on or turned off? It's turned on because it is a P transistor with a bubble, so low means on. So this is turned on. How about Q2? It's coming from Y, it is on too. What about Q3? Off. Q4 is off as well. Okay. So what is going to be presented as the output? Okay, so the output is, the circle pin here, right? Do we have connections to the high voltage?
Yes.
Yes, because both of the transistors connecting to the high voltage, they're both on, which means those valves are connected. So we have a path going from the output pin to the high voltage source. What about going to ground? Q3 is off, Q4 is off as well. When a transistor is off, the valve is disconnected flow, so we do not have a path. These two transistors are not connecting. Okay? So what do you think the output is going to be? Is it going to be a high or a low?
High.
It's going to be a high because we have two paths to connect to high. But we have no path to connect to low. Is that okay? All right. So the next one is a 1 and a 0. Okay, so if X is a 1, is Q1 on or off? It's off. Very good. What about Q2? Q2 is still on because Q2 is controlled by Y and not X. What about Q3? Q3 is on because Q3 is controlled by X, but because it's an N transistor, a high voltage would turn it on. Okay. What about Q4? Q4 is off because Q4 is controlled by Y, and Y is still 0 in this case. And for an N transistor, if the input is low, it is off. Is that okay? All right, so the question now is, what is going to be the output?
High.
The output is going to be high. Okay, well, but don't we have kind of a path to ground too? Nope, because the two transistors connected to ground, Q3 and Q4, are connected in series, which means if at least one of these two is off, the path is cut off. Okay, but going high, Q1 and Q2 are connected in parallel, which means if at least one of these two is connecting, we have a path. Yes?
Is Q4 on?
Q4 should be off because Q4 connects to Y, and Y has a value of 0 or low, and because it's an AND transistor, if the gate voltage is low, the transistor is turned off. Okay. All right. So the output is a 1 in this case. Now the next one is pretty easy, 0, 1, which is the opposite, but it's symmetric. So that means this is going to be on, this one's going to be off, and this one is going to be off, this one's going to be on, and the output is 1, okay, because we are just looking at a mirror image of the previous one. And a 1, 1 here means Q1 is off, Q2 is off, because they're both P transistors. When the input is a high voltage, the transistor is turned off. But both Q3 and Q4 are on in this case, so the output is going to be a low, because we lost both paths to go to the high voltage, because both Q1 and Q2 are off, they're not connecting. But at the same time, we have Q3 and Q4 being on at the same time, and they're connecting in series, so now we have a path to go to the ground voltage, which is the low voltage, or 0 in this case. Sound okay? All right. Yep.
So the whether it's on or off is coming from the high voltage at the top, and we're controlling whether that tap gets through.
Right. So if you look at this as water valves, this is your finger controlling whether to turn on. This is your control signal. And a P channel means, okay, if you push the button, if you do not push the button, it is always allowing flow. When you push the button, it is stopping flow. And then the N channel MOSFET is the opposite. When you push, it allows flow. When you release, it stops flow. Okay? So you have one single button controlling these two valves. You have another button controlling these two valves. So you only got 2 buttons. And then you have a cup up here. And then you have a collector down here. And the question is, is this going to here, or are you going, or is water going from here to here? Yep.
What's the arrow on top?
The arrow on top. You mean this one?
Yeah.
It is. It's called a power, symbol, or VCC. It's just representing a positive voltage. Yep.
And these circuits can vary, right? It's not exactly like this. It can vary, like you have the Q5, Q6 too.
Well, this is the minimum number of transistors to make a logic gate.
So it can be more.
Can be more, yes. So it can make a more interesting gate, but this is a minimal gate, and it is a very useful one too. Okay. So what we want to do now is to look at the truth table: x, y, and then x, blah, y. Okay, blah being an operator, just like logical and logical or in your C, C++ programming language. But we don't know quite what to put here in place of blah, so I'm just calling it blah. Okay. So the truth table is already here. We just did the truth table itself, but I want to just concentrate on the output and not really care about Q1 to Q4 because they are just the implementation of this type of gate. So they're not as important now, that we are just focusing on what should we put here. Okay, so when you look at this, it looks like it's kind of like an AND gate, but not an AND gate, right? Because with an AND gate, when both inputs are 1, it has one particular state, but if at least one input is not a 1, it is the other state. Yep, this is like an AND, except it's negated. Exactly, you guys got it. This is a NAND gate, AND A and D, which stands for negated AND gate. Okay, very good, good job. So this is a NAND gate, or you can use a NAND operator instead. Now, for those of you who insist and go like, I don't understand this, it's the same thing as that. It is the negation applied to the result of a conjunction or an AND. Is that okay so far? So there are several ways to represent, a NAND gate, but it's really hard to do it using a text editor because I don't have access to those, symbols. Okay, so now that we have a NAND gate, you go like, oh great, we have an operator that we don't even implement in all popular programming languages, right? You got AND, you get OR, you get NOT, but you don't have NAND. You even have exclusive OR, bitwise exclusive OR, but we don't have NAND. Well, as it turns out, NAND is all that you will never need. This is the operator that operates them all. Kind of like a ring that controls all the other rings. A lot of the rings. A lot of the operators. Okay, so how can that be? How can that be the case? So let's see what happens when you just want a simple negation. Okay, a simple negation of X. How can we use NAND in this case? Right? X NAND X is just the negation of X. Okay, cool. What about just regular X and Y? Okay, how do we express that? Well, how about this? X NAND Y NAND X NAND Y. Because we are negating X NAND Y, but we know that negation is just applying the same thing to both sides of the NAND, right? Okay, this one's got to be a stumper, right? How do we do OR? See, OR is not even a part of NAND. How do we do this? You use De Morgan's law. Okay, so what you do is you say, okay, I know how to do this. Would anyone dispute this? Other than, it's not the best way to say it. Not X or Y is the same thing as X or Y. Great. But now we can do something fun. Because now we can say, oh, I can regroup these things a little bit, like that. I'm just, imposing the order of evaluation here. No big deal. But once we get to this point, we can apply De Morgan's law. Now, De Morgan's law is really cool. It's kind of like distributing negation into the inside of a conjunction or disjunction, but by doing so, you have to change a conjunction to a disjunction, or a disjunction into a conjunction. Okay? So in this case, we are going to say, oh, so we are distributing the negation to the inside, like that, but we also have to change the disjunction, disjunction here into a conjunction. Oh, wait. Isn't this the negation of a conjunction, which is NAND, right? And we also know how to do this already. So just to be complete here, this will become, it becomes X NAND X NAND Y NAND Y. Yes, so NAND is all you need. Now we can go back to, in fact, I can tell Mr. Fox right now, right after this class, and go like, why are we teaching 3 logical operators when you only need 1? Okay, so we are running out of time. We are going to room 128 for the lab portion, and there is a lab to kind of, I'll do something in the lab and you can follow along, which is, oh, let's make this happen. I'm a maker, okay? I like to do stuff. So how do we, instead of just reading about it and just theorizing everything, can we make this happen? And the answer is yes, okay? So I'll show you guys how to do it, because this is the tool that we'll be using for the entire semester. So I'm going to show you guys how to do this in a simulator. So I will see you guys over there in room 128.